Our first talk of the session is entitled Blockspace Under Pressure, an analysis of spam MEV on high-throughput blockchains, and the speaker is Wenhao Wang from Yale and IC3.
All right, thank you, Ari, for the introduction. I'm Wenhao. I'm a third-year PhD student at Yale, and I'm very happy to present our work, Blockspace Under Pressure, and as a spam MEV on high-throughput blockchains. And this work is in collaboration with Aditya, Lioba, Kushal, and Fan. And part of it was done during the summer research internship at Category Labs last summer. So yeah, let's get started. So spam consumes a lot of block space in existing high-throughput blockchains. And what are spam transactions? They are essentially transactions that got reverted a lot or does nothing on-chain. So as you can see from this figure, around 25% of block gas on base Arbitrum was consumed by spam last year. So this was the statistics of base. And you can see that at its peak, around 50% of the block size, entire block, is taken by those spam transactions. So it's such a thing. So which makes the contract is that only less than 2% of them will result in some useful state changes like a trade on some DEXs. So, but what are spam transactions? What are spam MEV? So in order to understand what spam MEV really are, you need to compare with targeted MEV. So in traditional targeted MEV, they're essentially a searcher who might be a bot, which does a lot of off-chain computation using the data they got from the public mempool and to see if there are any profitable opportunity. If any profitable opportunity appear, then they will submit exactly one transaction to the chain, and with high probability, this transaction will succeed and they'll receive some profit out of it. So some examples of such targeted MEV are, for example, sandwich attacks and maybe liquidations on public blockchains like Ethereum. So in contrast, spam MEV are different. They present a completely different execution strategy. So in this case, there's a searcher. They do not perform targeted searches off-chain with the data they get from mempool. Instead, they just submit a lot of transactions on-chain, hoping one of them will grab some value. So this is what it does. They just flood the blockchain with a lot of transactions. For example, they may query for some of the prices and price difference between two DEXs and to see if there are any profitable chances. And because the on-chain execution is very cheap on some of the blockchains, even if most of these probes, most of these transactions fail, it is still profitable for such searchers. A very few of them will result in a profit. So an example of this is what I just said. You just query the price difference among multiple DEXs and to see if there are any profitable arbitrage opportunities. So what makes this spam MEV strategy prevalent? So I name a few here. Firstly, is the low transaction fee. On some of the blockchains, the transaction fees are really low so that it's profitable even if the success rate for such strategy is really, really low. So this is one of them. The second enabler is fast block time. On some blockchains, the block time is really small so that you don't really have the time to perform these targeted searches to do all of these off-chain computations. And then submit it. You just don't have enough time, so you have to resort to some opportunistic searches on-chain. And the third enabler of such strategy is the lack of public mempool. Without the public mempool, it's very hard for you to first identify an opportunity off-chain. You have to do it on-chain. So yeah, with this, we actually have a lot of examples of the blockchains that has such spam MEV behavior. To name a few, we have Base, which has a very low gas fee, and a very small block size, which is around 200 milliseconds with when flash block are enabled, and they do not have any public mempool. And also we have Arbitrum, which is another layer 2 that also has low fee, small block time, and the lack of public mempo as well. And to name layer 1, we have Solana, which has low fee and relatively small block time, which is around 400 milliseconds. And they don't have a public mempool where you can perform targeted searches. So in order to understand what makes this spam MEV possible and what shapes their behavior, we need to understand, we need to pick out some of the possible parameters. And let me give you an example with this statistics that we did. So firstly, spam volume is affected by the block size. So we ran some statistics on the Base and Arbitrum blockchain, and this is the numbers we got from Base. So Base adjusted its block size from time to time, and we see that after Base raised its gas target, which essentially is the block size, the spam MEV volume grew by more than 100 times, while the non-spam volume only grew by around 10 times. So there's a huge discrepancy here. And there's one time when Base cuts its gas target from 70 million to 50 million, the spam MEV fell by 34%, while the non-spam volume only fell by 24%. So there's also a difference, which means that spam MEV is, the volume of spam MEV is more sensitive to the block size than the non-spam volume. But why? Here's another parameter that shaped the behavior of spam transactions on chain. So this is what we call the minimum gas price, which is some chains, they do set a minimum gas price which each of the transactions has to pay. So Base, for example, introduced it in December 2025 and racing across multiple steps. And after these measures are believed to be taken because they want to mitigate spam somehow. And we see, as a result, the share of the spam transaction fell from around 26% to below 9%. So in contrast, the non-spam gas is almost not changed after such changes, which means that spam volume is susceptible to the minimum gas price increases. So, so now I introduce two parameters that may shape the behavior of spam transactions and eventually affect its volume, which are firstly Bmax, which we call the block size, which is the total capacity that is available in each block. And secondly is what we call Gmin, the minimum gas price, which is the floor of the gas price each transaction has to pay, and independent of the availability of the block. So even the block is very empty, the transaction has to pay such a price. And also, as we'll see later, there is the transaction fee mechanism that also affects how the spam transaction behave, because the transaction fee mechanism, which is the TFM for short, affects how the transactions are priced and ordered within each block. So as we have identified some of the potential candidates for what shapes the spam, I'm going to talk about a little bit about the model that we use in order to proceed with our analysis. So firstly, I'm going to introduce the user demand model. So we assume that different users may have different valuations of the transactions that they have on each block, on the block. So let D of G denote the total gas demanded by the users with valuation G or higher. So here, for the to make it easy for our analysis, we assume the linear demand function. But we note here, as you can see from our paper, is that our result also hold qualitatively for more complicated demand functions like the exponential demand. But now in the presentation, I'll do it with the linear demand function. So now we are trying to understand how the spam volume is spam transaction will behave. So I'm going to introduce what we call the comparative spam equilibrium, which means that the spam transactions will enter the blockchain until the utility of each spam transaction will approximately be 0. So let S denote the number of spam transactions, and the U of S denotes the utility of each spam transaction. So here we model that when the utility of each span transaction is greater than 0, since blockchain is permissionless and anyone can join to submit a transaction, so more spam bots will flood until they reach a point where the utility of each span transaction will be approximately like 0, so they don't get a lot of value out of each span transaction that is submitted to the blockchain. So this is what we note as comparative equilibrium. So, which is an important assumption that we make for our analysis. So now we can finally analyze something. So I'm starting with an easier transaction fee mechanism, which is the random ordering TFM. So it means that the TFM will set a gas price G of the blockchain by clearing the supply with the demand. And after TFM settles which transactions are included in the block, every transaction are randomly ordered. So you don't know where you'll be ordered when you submit the transaction, essentially. And we assume there are like MBV opportunities for these span transactions to grab on chain. So for each of these opportunities, it will be captured by the first span transaction that is scheduled or ordered after the opportunity. So we also assume that the size of the opportunity R is proportional to the included user transaction, as opportunities will pop up as users submit their transactions. So with a single opportunity, as I use this illustration here, let's assume there's a single opportunity and 4 span transactions. So what will be the utility of each span transaction? So since everything is randomly ordered, you'll see that since there are 4 span transactions and 5 equally likely positions where the opportunity may lie, so the probability is that this opportunity is captured by at least one of these span transactions is 4 over 5, which is S over S plus 1. So with this, we can derive the utility of the span of each span transaction at the volume S. U of S will essentially be the expected revenue, which is R over S plus 1, minus the inclusion cost, which is the gas taken by each span transaction times the gas price. So this is the case with a single opportunity. What our model actually does is that it also generalizes to multiple opportunities with this aggregation lemma, which essentially is saying that under this random ordering, multiple opportunity will behave the same as the single opportunity case. And is a very intuitive proof by the linearity of expectations, since you can see here that the expected value that's captured by at least one of the span transaction is the expected value of each of them. So you can use this linearity to do the proof. And eventually, it leads to the result that the utility of each span transaction is not changed. So this expression is not changed, no matter how many opportunities you have within a block. So with the comparative equilibrium model that we brought up previously, so the US will essentially be equal to 0 at equilibrium. So we can solve this equation and derive what S will be in the equilibrium case. So we have this equilibrium figure which I divide into three regions. The first region in blue is the no-span regions, which means that there are like very small blocks, so that's the opportunity size is very low, so no span will really enter the blockchain because it's not even profitable for them to do so. The second region in orange is the congested region, where the span will enter and compete with the users to try to grab the opportunity. So some users will essentially be crowded out because of the existence of such span transactions. The third region in green is a slack region, which means that everything will fit into the block because the block is so large at the minimum gas price. So essentially, every user that should have been included in the block at the minimum gas price will be included. So then it comes to the question, given this, what should we do to pick the block size? So there's a baseline rule here, which is just to select the leftmost part of the green region, of the select region, scale until the block size reaches what we call B-plat. So there are pros and cons with regard to this. The pro is that the span volume will plateau, which means that this is the optimal since no users are crowded out. But the cons that if you select this parameter is that essentially it makes more spam. Essentially, it makes the maximum amount of spam that is possible here. So it suggests us maybe there is a better rule out there that the designers can pick. So to know what the better rule may look like, we look into how much of the marginal block capacity goes to the user transactions and the spam transactions. So this figure plots the share of the marginal block capacity that goes to spam is strictly increasing as the block size increases. So we can actually, by this, design a refined rule to select the block size. So this is to scale when at least either of the marginal block capacity goes to users. So I pick up some sample parameters here of different choices of eta. If eta, for example, equals 40%, which means 40% of the marginal block capacity goes to users, it will reduce spam by 27% when compared to the B-plat rule, the baseline rule, and the welfare loss is only 6%. And when eta, for example, equals 80%, then you reduce spam by 82%, while only resulting in a 40% of the welfare loss. So the takeaway here is that if you are willing to forgo a small amount of user welfare, it will decrease more spam and reduces the operational cost because the block size is essentially smaller. So this is analysis under the random ordering rule, and we also ask how different transaction mechanisms will shape the behavior of the spam. So we also did some analysis under the priority fee ordering, which a lot of chains will adopt. So here we are using an approximate model, which means that the blocks are divided into n subblocks, each with their own clearing price and random ordering within, so we can reuse part of the analysis we used in the random ordering TFM. So the earlier subblocks will have higher prices because the users with higher willingness to pay will be included in the earlier subblocks. So as we can see from this figure is that because the earlier subblocks are more expensive, they're essentially less spam compared to the random ordering transaction fee mechanism. And we actually also did some empirical analysis on base to validate our theory. So we're using the data gathered from base before the adoption of flash blocks. So we can see that only 41% of spam land before the median part lands in the first half of the block, which means that there are fewer spam in the earlier parts of the block, which is consistent with our model prediction. So finally, we asked about the scaling paradox. So last year, the researchers from Flashbots, they conjectured that when blockchains scale up, effective throughput will essentially goes to spam. The effective throughput here is that the gas that goes into real user transactions, authentic user transactions. And this is the figure that they had in their report, where the widening gap is essentially the spam transactions. So we want to see if this is true with our model analysis. And our result is that the spam share will stabilize as the chain grows. And we agree that there is a widening gap, but the takeaway here is that the share of the spam transaction will remain stable if you choose the parameters of the blockchain accordingly as the user demand scale. So maybe this is the price you have to pay for high-throughput blockchains, that parts of the effective throughput will essentially go to spam transactions. So because of this, we ask if there are any possible mitigation to spam. So we categorize them into two different broad categories, which are like system-level mitigations, which is essentially how you design or pick the blockchain parameters, And there are also like application-specific mitigations, which is like how you redesign some of the specific decentralized apps. For example, the DEXs, how do you redesign the mechanisms in order to reduce the size of MVV opportunities? So within the system level mitigation, we named two. Firstly, there is like incentive-based mechanism, which is increasing the expected cost of spent transactions. For example, you might want to increase the minimum gas price. And secondly, there are cheap pass mechanisms, which essentially makes the failed spent transactions is cheaper to execute on blockchain level. So both of them are possible. And we do see that with some of the measures taken, you do actually reduce the spent transactions on chain. For example, this is what Base does, as I mentioned earlier in the talk. They increased their minimum gas price across multiple steps in December last year. So after they took this measure, the spam share fell from around 26% to below 9%, while the non-spam gas volume essentially remained approximately not changed. So yeah, this is everything from my talk. And please scan this QR code for the full paper. And I'm very happy to take questions. Thank you.
Hey, any questions for the speaker?
So you do static demand, basically? So you assume it's stationary in your model?
Sorry, I cannot really hear you.
Sorry. You assume the demand for Blockspace is stationary or constant. That's not really true, right? So it's... And also there's endogeneity, right? So the demand in one block should influence, demand in the next block and also the price in the next block and these kind of things. So how do you, how realistic is your model and what would it change if you add dynamics to it?
Yeah, I mean, that's a limitation of our model. So we are modeling a static demand case, like we are analyzing within a single block instead of like the continuous multiple blocks. I think it will be interesting to see how the spam volume will fluctuate across the adjacent blocks. It will be interesting future work.
Okay, well, perhaps I can ask a question. This is really interesting work, in part in that you're basically showing that classical mitigations like encrypted mempools and fair temporal ordering just don't work in the current regime. But your measurement study presumes the ability to identify spam transactions. Could you mitigate spam transactions by identifying them and penalizing them in some way?
Yeah, that's a very great question. We also ask this question a lot, but it's kind of tricky here. Let me give you an example. It's like, for instance, how we classify these spam transactions is like they bring no state changes and they are interacted a lot. But if you just penalize such transactions, then these bots can do a very simple thing to avoid such penalties. Like they can just transfer a tiny amount of money to some random accounts in order to make some state changes so that such classifiers doesn't work. So yeah, it would be very interesting to see what are some good mitigations so that they are disincentivized apart from the increase in the minimum gas price measure I just talked about.
Okay, let's thank the speaker again.